deals with applications of differentiation. And you can say, but what was logarithmic differentiation? What were related rates all about? What was the thing with the differentials all about? Were these not applications of differentiation? Yes, they were. Yes. But now we have 3 topics in this chapter to look at. They are also applications. All these are applications of differentiation. But we are going to look at, in chapter 4, 3 major topics, huge topics. So actually 2.5, if you want. Graphing, functions, major topic, with all sorts, with holes in them, asymptotes, basically infinitely many different functions, combinations, infinite functions. Can we deal with that? No, we're going to just stick with some of them. What is the second major topic? Optimization. Optimization deals with finding max-min. And the last tiny topic that it's a very important application of differentiation is Newton's method. To explain this, as I mentioned in the study group, I probably need 5 minutes. It will take longer to enter the data or the function in the graphing calculator, but this is a very small topic, extremely powerful, but very easy. So this is like a huge topic like related rates. I really need a month on this, so we're going to use an hour or 2 and stick with just the idea of, simple examples and how we find max-min in real-life situations. And this will take quite a while because we have a lot of things to talk about. And there are some other minor topics like the Rolle's theorem and the mean value, this is an E here, value, L-U-E, theorem. Okay, so in 4.1, we're going to look at max-min. So, of course, of functions. How do we find max-min? And they are of 2 different types. Something called relative, also called local, same thing, max or min, and something called absolute, also called global. They're interchangeable. So in some books you're going to find is relative, in others you're going to find as local, absolute, or global. It's not important, as long as we know what we're talking about. So I'm going to talk about the difference between the 2 first. I'm going to graph a simple function. Something like this. Let's say it starts here, and it does this. So here's a function. By the vertical line test is a function. And obviously, the function is increasing till this point, where we know the tangent line has a slope of 0. And then it's decreasing till this point, where we see that the tangent line has slope 0. And then it's increasing till this point. Okay. Now, if we graph a couple of tangents here, and a couple of tangents here, and one here, we realize that clearly, when the function is increasing, the slope of the tangent line is positive. When the function has a peak, the slope of the tangent line at that point is 0. When the function is decreasing, the slope of the tangent line is negative. And again, here it's increasing, so the slope of the tangent line is positive. This point, I'm going to call it point A, and this is point B, and this is point C, and this is point D. Point A is a local max and also global max. For local, for a function to have a local max, the function must exist on both sides, and the function values in this tiny interval are all smaller on both sides, smaller than this function value. Then this point is called a local or relative max. So I have to have the open interval, the function must exist on both sides, and all function values are smaller than this particular height. Therefore, this is a local or relative max. In my example, this is also an absolute max because the function starts at C, ends at D, doesn't have arrows. So this is the absolute maximum value of the function. Point B is exactly opposite, but the same thing. It's a local or relative min. It's a global min. B. Relative min, global min. Okay, what happens at the endpoints? Endpoints are never local. Why? Can anyone tell me why the endpoints can never be local?
Because nothing's coming from both sides.
Exactly, because we just said I cannot show the open interval. So I can show the open interval, but the function does not exist on this side. Therefore, it does not fulfill the conditions of a local. However, the endpoints can be absolute. So here's an example. So this is in this situation the local min and the absolute min, but this is only the absolute max. So absolute and relative min. And this, nothing. Because it cannot be relative, and it's not the smallest, and it's not the highest. So here, C and D are nothing. Nothing. They're points, but nothing to write home about. Okay, I would like to share my screen and go to the book. Where is my book? I got it. Almost there. Oh, where is my book? Here's my book. So let's go to 4.1, and I'd like to look at some graphs and analyze local, relative, yada, yada. Okay. Okay, so if we want to look at this graph, what about S? What can you say about S? What does the function have at x equals S?
The absolute max.
Absolutely, yes. What does it have at R?
Relative and absolute.
Absolutely, yes, correct. Correct, very good. And here at C,
Relative max.
relative max, awesome. What about B?
Relative min.
Excellent. What about A?
Nothing.
Nothing. What about D?
Nothing.
Exactly. Okay. What about this point? 1, so 2, 4, 6. Let's analyze what happens here at 6.
Would that be a relative max?
Correct. Because the point exists, the function exists on both sides, and all function values are smaller than it. What is it? 1, 2, 3, 4. So the function exists on both sides, and the function values are smaller than it. This one, if it were up here, I would have said it's a relative max. Sorry, I forgot to turn off my phone. Sorry about that. So if it were, for example, anywhere up here, I would have said it's a relative max because I can show the open interval, and the function exists on both sides, and the function exists on both sides, and the function values are smaller than it on both sides. But because the point is here, I cannot say it's a relative max, and I cannot say it's a relative min. Because if it's a relative min, all function values left and right have to be higher than, what is it, 1, 2, 3. But they're not higher than 1, 2, 3. Okay, so for example here, this is a relative min. The point exists, and the function values, the function exists, in other words, also, point exists, function exists left and right, and all function values are higher than it, which is 2, height of 2. Okay, I think we got the idea, so we can move on to the next topic. Any questions for me? Any questions? Okay. Now, no, this was 3. Okay, so we're going to choose, we can look there, or my book is easier for me to get to 4.1. And I like to choose a function and talk about something called critical numbers. But I'm going to choose a function, or if you want to, you can choose a function. Choose. We're not going to sketch any graph in this section. No. So when I assign homework from this section, please disregard sketching. We're not ready to sketch anything other than very simple functions. So yeah, you can, natural log and so on and so forth, but anything more sophisticated, no. Okay, so I'm not asking you to graph. Yes, you can graph something like this and basic functions, but if they ask something like graph this, no, or graph this, no, we're not ready to do any of that yet. We will. Okay, so any preference, or I will choose? Okay, I want to start with, let's say 35. 35 has g of y equals y minus 1 divided by y squared minus y plus 1. Now, coming back to these little graphs, so what have we noticed? So we notice that the function has a maximum as long as on the left-hand side is increasing and on the right-hand side is decreasing. On the left-hand side, the derivative is positive. On the right-hand side, the derivative is negative. It has a relative minimum as long as on this side the function is decreasing and on this side the function is increasing. In other words, the derivative is negative and the derivative is positive. So something called critical number can change, only critical numbers can change, or if you want can become or may become, that's enough. So it can change into max min. And I said can. In other words, no guarantee. There is one guarantee though. If there are no critical numbers, Cn, f of x cannot have max min. That is guaranteed. This is guaranteed. No critical numbers, no max min. If critical numbers or critical number exists or critical number exists, the function may have max min. No guarantee. But there is a guarantee if it doesn't have critical numbers, it cannot have max min. Okay, so now what is a critical number? Critical number or critical numbers come from two possible sources. Here's one, here's the other. Function may have critical numbers coming from both, or from one, or from the other, or none at all. So critical numbers come from two possible sources. One possible source is from f prime of x equals 0. I solve the equation, and let's say I get a equals whatever. This is a critical number. I may get x1, I may get x2, whatever number, and I get another critical number. So this equation, if this equation has solutions, then the function has critical numbers. If this equation has no solutions, the function has no critical numbers. What is the second source? Second source is when the derivative is undefined, but that's not enough, at a point, and I'm going to say points, where f of x is defined. Because if the function is not defined, I don't care if the derivative is undefined. Who cares? If the function doesn't exist, we don't care that the derivative is undefined. But if the derivative is undefined at a point where the function exists, then at those points or x values, we get again critical numbers. So bear with me, I want to go back for a second. Here. Which problem? Yes, here, the first one we talked about. Is there any particular point on this graph where the function exists, but the derivative does not?
B.
Say it again.
B, point B.
B as in boy. Excellent. Why? Because the function has a...
Is it a cusp or is it a
cusp. Excellent. So at this point, this will be a critical number for the function. Why? The derivative does not exist. The function does exist, and it will be a relative minimum. Here at this point, the first derivative will be 0. And the derivative here is positive. The derivative here is negative. That's why this is a relative max. So this is what I'm talking about for f prime being undefined, and this is what I'm talking about f prime being 0. But f prime being 0 or f prime being undefined does not guarantee a max min. Only if the derivative changes sign. See here the derivative is negative, but here the derivative is positive. So that's why this is a relative min. So here this is a critical number. Is there guarantee that it's a max? No. Unless on the left-hand side the derivative is positive and on the right-hand side the derivative is negative. Then it is guaranteed that this critical number becomes a max or gives a max to a function, to the function. But what about, I don't have an example. What about in this situation? For x cubed. At this point, I guarantee you that f prime of x will be 0. So, which is x equals 0. How do I know? Well, because you want to differentiate, you get 3x squared. So x is 0. And that will be a critical number. Look what happens. The derivative doesn't change sign. So this point, or x equals 0, although is a critical number, it will not change into a max min because the function is always increasing. It's not increasing and then decreasing to create a max here. So critical number, but no max min. Okay, now we're going to choose several functions and go through this procedure. What procedure? Finding critical numbers and analyzing if those critical numbers, if they exist, if they turn into a max min. Okay, so before that, I just want to say one